Hello, my name is Pedro Martins. I'm here to present my thesis, a PX4 ROS to Avionics architecture for the E-rocket, thrust vector control and GNC platform. My supervisors are Professor Paulo Oliveira and Masters of Science Pedro dos Santos. Now, starting from motivation. Rockets are very cool, but they are very hard, and they have one problem. They're highly unstable. So what's the solution? Guidance, navigation, and control. This is a branch of engineering that designs systems to control movement of vehicles in real time. Guidance essentially tells the vehicle where it wants to go. You can think of it as a trajectory. Navigation tells it where it is. You can think of it as position and orientation. And then control actually makes this happen by controlling the actuators on the vehicle. Now, in order to develop GNC systems, simulations are indispensable because but simulations only approximate reality, and so it's always important to validate GNC systems in the real world. Now, how do we control rockets? We need an actuator to have an effect on the rocket. That's where thrust vectoring control comes in. By redirected engine thrusts, you can control its orientation, position, and trajectory over time. Now, advancements in commercial electronics have democratized access to electronic computers. This is widely used on research nowadays, and it allows researchers to develop all sorts of different vehicles. In terms of rocket research, several research groups have been developing some small scale electrically powered vehicles that mechanically behave like rockets but are safe and cost effective by comparison, and they serve the purpose of validating guidance, navigation, and control algorithms. And so, validating algorithms in these vehicles can be analogous to validating them in full scale rockets, which are usually more complex, expensive, and require greater safety concerns. Now, there's been a recent project developed at Instituto Superior Técnico by a brilliant research team. That's the E-Rocket project. The aim is to develop a small-scale electric thrust vector control rocket that will be used to validate new GNC algorithms for rockets. Now, my thesis is on designing and implementing its avionics. So I contributed by doing exactly that, designing and assembling the e-rocket avionics by developing a custom software stack that runs the necessary guidance, navigation, and control software. I also validated the architecture on the e-rocket by demonstrating its suitability as a research platform for thrust vectoring GNC development. And I also provided a public release of software and documentation. Now, looking at the state of the art, the industry avionics are usually closed, expensive, and proprietary. So most modern research platforms end up using hobby drones for their electronic components. But there's a problem here. Drones don't behave like rockets, and so their avionics don't work out of the box and need to be adapted. They usually have a combination of a flight computer and a companion computer. Now, the flight computer is responsible for flying the drone. The companion computer adds features onto the drone. Features can be vision models, mission logic AI models, and experimental guidance, navigation, and control algorithms. And in terms of software, on flight computers, they usually run open source software. They're usually real-time operating systems running on a microcontroller, which is a type of computer that's very task specific. Now, this system also supports a wide array of hardware components. Now, the companion computer is usually a general purpose operating system like Linux, and it usually runs a robotics middleware, which is a middleware used for complex robotic systems. They essentially abstract away all the hardware complexity and they easily integrate new technologies with it. And so it essentially helps simplifying the software design. So looking at the state of the art, there's a big gap where there's no ready to use, affordable thrust vector control rocket avionics for validating GNC. The conclusion here is that research teams have to build the avionics themselves. So that's what we did. Now, these requirements came from the research team, and they required the rocket to be lightweight, safe to use, the software to focus on the modular integration of GNC algorithms, and also provide a fast development time with an iterative design. Looking at the hardware layer, We have sensors, actuators, and different peripherals. They're all connected to the Phi computer, the PX4. The Phi computer then uses the middleware bridge to communicate with the companion computer. Now, as I mentioned before, the Phi computer runs the drone, and in our case, the ROS2 runs the GNC algorithms. And we have the ground segment layer, which essentially monitors both Phi computers and it acts as an operator interface. Now, for the hardware architecture, commercial electronics, we only used commercial electronics for the hardware because they have proven reliability. They're commercially available and they support auto-powered software we used. And so this allowed the team to focus on the software and guidance, navigation, and control, and not the hardware development. We will analyze these diagrams section by section, starting with the proportion and thrust vectoring control mounts. Now, the motors were the first components selected because they dictated the maximum weight of the vehicle and also the flight times. Now, we use two counter-rotating motors with the custom aluminum mounts. In terms of servos, we use two servos, one per axis, perpendicular to each other, which provided 2 degrees of freedom. And this essentially was our thrust vector control system. Now, for our Phi computer, we use the PXOC 6C Mini. It is compact and light. It runs the PX4 autopilot. It contains onboard sensors, but it also supports GNC and motion capture systems. Which are used for the GNC is used for outdoor positioning and the motion capture is used for indoor positioning. Now, the companion computer was a Raspberry Pi 5 with 8 gigabytes of RAM. It has Wi-Fi support and it also runs Ubuntu with ROS2. Now, the middleware bridge is composed by two cables for independent connections from the Phi computer to the companion computer. And we also had the radio control system acting as a kill switch to disable the motors for safety. You can see the radio control transmitter and the image right there. And we also had, as I mentioned before, a Wi-Fi connection to the ground segment. Now, in terms of power, we used lithium polymer batteries, which have a high capacity and high discharge rate. They have decent amount of mass, and they also provide about 3 minutes of flight time. Now, this battery is connected to the power board, which distributes the power to all motors. And the power module and the ESCs contain what is called the battery eliminator circuit, a BEC. And the BEC essentially powers all the peripherals, the servos, and the Phi computers. Now, looking at the software, what you see there is a context diagram, which essentially tells you how the software is used. So first off, the software is used to acquire sensor data. Then it executes the guidance, navigation, and control algorithms. It then actuates the thrust vectoring mechanism and motors. And at the same time providing and maintaining communication with the ground segment and the motion capture system. So we have three types of users in this system. The mission operator, which essentially sets up all the missions and monitors missions during flight testing. The guidance navigation and control researcher, which essentially implements and fine-tunes all the algorithms, all the GNC algorithms. And then the safety operator, which essentially uses the RC transmitter for safety as a kill switch. Now, some approaches to implementing this architecture were considered. The first one was a custom software from scratch, which was deemed impossible for the Thesis timeline because of the amount of complexity of the system. We also considered modifying an open source autopilot, but the autopilots usually have massive code bases with steep learning curves, which made it hard for implementing any new GNC systems, not only for me, but also for any new aerospace engineers that joined the research group. But so we ended up selecting a hybrid approach where we used the flight computer with an open source autopilot called PX4 and provided minimum modifications to it. And then we also used the companion computer, which was running a robotics operating system, which essentially was the software we designed from scratch to allow the GNC researchers to implement their algorithms. Now, This is essentially an overview of the hybrid approach. What you see here is the GNC modules. In gray are the modules that are disabled, and in green all the modules that are active. And so what you can see here is that instead of using the PX4's built-in GNC algorithms that are fine-tuned for drones, we disabled those and instead implemented our own algorithms in ROS2. And so this is essentially how the hybrid approach works. We had part of the system running on PX4 and part of the system running on ROS2. We talk about GNC later, but for now, let's go dive into the software architecture. So what you see here is a detailed view of the architecture, all the modules and all the interfaces between them. Now, looking at PX4, PX4 provides real-time guarantees, and we only use the subset of modules. First off, there's a sensor hub which provides sensor data. Then the estimator estimates the rocket's position and orientation. The finite state machine is used to arm and disarm the motors. It also runs all the safety algorithms and also the any modules transitions that happen within the state machine running on PX4. We also use the micro XRC DDS client is essentially a bridge that allows the communication between the ROS2 and PX4. And the MavLink module is just to allow telemetry between the PX4 and the ground segments. Now the PX4 provides native support for ROS2, so there was no need to implement any code on the PX4 side. Now on the ROS2 side, we developed all of these from scratch using ROS2 concepts. And so instead of talking about nodes, topics, messages, and services, I'm going to be referring to them as modules and interfaces. So looking at the flight mode module, the flight mode module provides a direct connection to the PX4's state machine and synchronizes the ROS2 state machine with the synchronizes the ROS2 mission faces with the PX4 state machine. We also have the mission module, which essentially runs the mission faces, that being like a state machine inside of ROS2, and using the fight mode module, it synchronizes that state machine with the PX4 state machine. I can go into further detail about this after the presentation, but for now let's continue. The controller module executes and implements all the controller logic, and finally we have the motion capture forwarder module, which provides support for motion capture systems for indoor positioning. Now, all these modules communicate using defined interfaces, and these defined interfaces allow for independent development of the modules. Now, we have 4 channels of communication. We have a real-time control channel, the micro XRC DDS, which connects the PX4 and the ROS2 to exchange real-time data. This real-time data is critical for stability and the operation of the rocket. So if this connection fails at any point, the rocket can't control itself. So it's critical to minimize communication delays, and so they're physically close and connected via cable. Now we also configured both systems to minimize latency and jitter, and we did timing analysis in order to verify the total round trip latency, and it did remain within the GNC constraints. Now, the MavLink module is used for the PX4 configuration and telemetry, and we also have telemetry and visualization for just the ROS2 network. And we also used an SSH client in order to maintain and configure all the ROS2 inside of the companion computer. Now, for safety is implemented in 3 levels. We have hardware safety using the RC kill switch, and by disconnecting the power. We have safety on PX4, which runs configurable failsafe actions. And we also have an off-board timeout, where if the connection between the PX4 and ROS2 is severed, in 1 second, all the motors are disabled on the PX4. And we also provide safety for ROS2 by running simulations of the ROS2 network before actually running it on the vehicle, and also by providing abort commands on the vehicle as well. And so what that means is that every level can disarm the vehicle, and the vehicle, in order for the vehicle to recover from this state, it requires explicit rearming from the users. Now, so in conclusion, this provides a deterministic safety model which guarantees the fail-safe behavior of the system. Now, looking at the configuration, build, and development, the PX4 was configured for specific hardware used, and so we ended up modifying the hardware, removing any unused modules and features. We configured the data exchange with ROS2, and we also compiled and flashed this software. Now, the ROS2, we used configuration files to configure the parameters for the modules, and we also used launch files in order to initiate all these modules. During development, we compiled and ran all the ROS2 on the development machine, but during flight tests, the ROS2 is compiled and run directly on Raspberry Pi. Now, we follow the single responsibility principle methodology. For methodology, we follow a single responsibility principle where each module is responsible for one thing and not one thing only. We develop well-defined interfaces. We follow the requirement-based strategy. We relied heavily on prototypes for decisions on design and implementation. We use iterative design for adding new features, and we also use the scientific method for debugging and fixing any problems we found along the way. Now, for implementation, the ROS2 was implemented in C++, but ROS2 is also supported by Python and MATLAB and other computing languages. For validation, we used unit testing, integration testing, bench, software in the loop, and flight testing. Now, back to GNC. The eRocket was designed with the explicit purpose of serving as a flexible research platform for guidance, navigation, and control systems. And so the research team created two controllers, one guidance algorithm, but they didn't develop any navigation algorithm, so we used PX4 state estimated. We had a baseline controller which was adapted from a project called Pegasus from the Institute of Systems and Robotics at Instituto Superior Técnico. From the two controllers the team developed, only one of them was flight tested, and we were going to call that the non-linear controller. And for guidance, we have discrete position. We can follow discrete positions in space, and then we can also follow continuous trajectories. All the frequencies you see on the diagram were set by the guidance, navigation, and control team and validated using flight campaigns. Now, this architecture provides modularity and extensibility. Each arrow you see there is an interface, and so these interfaces were developed to be generic. And so what that means is you can extend and replace the modules you see on ROS2. So you can develop a new state estimator only on ROS2, or you can change the existing guidance and controller algorithms. So essentially this gives freedom for the researchers to implement different solutions. You can use Python and C++ libraries, so that means using computer vision models, AI models, all that sort of stuff. It also supports MATLAB Simulink in order to that essentially generates the code of the modules using a user interface. Now, we actually proven this system is extendable because we implemented simulated nodes on it, where essentially we replaced some of the modules with simulated modules. On the left side, you can see the ROS2 nodes. They are usually active during a flight, and on the right side, the simulation counterparts. We can go into further detail about this after the presentation. Now, we started developing a minimum viable product. Oh no. Oh, never mind. Developing a minimum viable product. The prototype has minimum features. And we use this to figure out if the PX4 ROS2 architecture is viable, and we used it also for the thrust curve. Now, we tested guidance, navigation, and control modules and the overall architecture using bench testing. The results demonstrated stable control, and also we used the opportunity to structurally test our vehicle, but importantly, we had a 3-week test campaign. The goal was to the goal here was to move the vehicle to specific positions in space. As you can see on the vehicle, we have some minor oscillations, but we also use this to test safety mechanisms and the GNC timing and frequencies in flight. Finally, we developed a 2-week test campaign for the non-linear controller. You can see there's a smoother trajectory following. There's a smoother trajectory following with reduced oscillations. We validated our takeoff and landing trajectories as well, and these experiments validated the e-rocket avionics system provides reproducible and extensible environment for the development of guidance, navigation, and control algorithms. In conclusion, the system fulfills all the set requirements and it works as avionics for validating the guidance, navigation, and control systems for thrust vectoring control rockets. For future work, the team has lots of ideas on how to move the project forward, which I'm happy to talk about after the presentation. Thank you so much for your time.